So I'm going to go ahead and talk a little bit more about acceleration when we have vector valued functions. So let's just talk about acceleration in general. So acceleration, right, is the change in velocity. I keep doing that today. Acceleration, right, is change in velocity with respect to time. Well, if we're thinking about vectors, remember velocity is a vector. That means it has magnitude and direction. And if you change either one of those, then you're going to feel this acceleration. So I'm going to go ahead and do a little Newton's laws on you here. So right, you all know, right, force equals mass times acceleration. So, right, I'm going to have you guys think about when you feel this force on you. Right? So if you can feel the force on you, that means there's some acceleration going on. Okay, so now let's imagine that we're in a car. Ignore this stuff for a second. So imagine you're in a car and you're on a straight road. So you're just driving on a straight road, right, in a straight line. If your velocity is constant, right, you have no change in velocity, you're going on a straight road, so you don't change the magnitude, you don't change the direction, you're not going to feel any acceleration. Right now, if you speed up, right, if you go faster, or if you slow down, right, then you will have this change in velocity, so you will feel some acceleration. So a straight road, in order to feel that acceleration, you have to actually change the speed, change the magnitude. Now, if you're on a curved road, right? So you're coming over, or you're coming on an on-ramp or an off-ramp off of the highway, right? Even if you're going at a constant speed, so let's say your speed is constant, so you're not changing the magnitude, but you are changing the direction, right? So that change in direction is also producing an acceleration, right? So you're going to feel a force, right? And the force that you sort of feel is pushing out this way. But the force on the car, right, is in towards the center. It's called the normal force. So as you go around this curve, right, if your velocity if the magnitude is changing as well, right, you can have a tangential component and a normal component. And these two together, right, will add up as vectors do and come up with the acceleration vector, the total acceleration. So your acceleration vector that we get by, right, taking the second derivative of our position vector or first derivative of our, right, so acceleration vector equals, right, the first derivative of the velocity vector or, right, the second derivative of the position vector. Okay. That vector for acceleration, right, will have its components, x, y, and z, right? X double prime, y double prime, and z double prime. Okay. But we can also break it into the components relative to, right, the tangential component, the unit tangent vector. So we'll get that magnitude a sub t in the t direction, the unit tangent vector. And then we'll have that normal component, a sub n, in the normal direction. So remember, so t, our unit tangent vector, this is just, right, the velocity vector divided by the magnitude of that, or the speed, right? You could also use your r prime things here. And then the normal vector, the unit normal vector, is the derivative of the unit tangent vector divided by the magnitude of the unit tangent vector. Get all my lines in there. It gets kind of messy. Okay, so remember this down on the bottom here. This is the speed. That's the magnitude. It makes that velocity vector have, right, unit 1. All right, so let's go ahead and let's do an example. And I have an r of t function, and we are going to find the components a sub t and a sub n, and then we're going to write our a vector in terms of t and n. So some computational things that we're going to find useful. So that a sub t part is equal to, the part of a that's in the direction of the tangent. But if you do a little manipulating right here, you'll see that that is a dotted with v divided by the magnitude of v. Okay. So this is a little bit more user-friendly. And then so usually we don't want to have to do this n part if we don't have to. Sometimes we will, but that's okay. Oh, my vector lines. Oh my gosh. So this a sub n, this is just the magnitude in the n direction. Magnitude in the normal direction. A sub t, this is the magnitude of the acceleration, so magnitude of acceleration in the tangential direction, so in the direction of motion. Okay. To get a sub n, the easiest way to do it is to take your a vector and subtract off that component, that's in the t direction. So it's the amount of a that's in the direction, of the normal vector. And it's actually do these all as magnitudes, So the magnitude is the magnitude of the total acceleration minus that a of t. Okay, I think you'll see it once we get going here. Here's our example. So r is t squared natural log t 2t. So we're going to find a sub t and a sub n at t equals 1, and then we're going to write our acceleration vector in terms of t and in terms of n. Okay? So let's go ahead and gather our pieces. We have r, so let's find v, our v vector. So we take the derivative, r prime. So that'll be 2t, 1 over t, and 2. Okay. And then we'll get our acceleration vector. So differentiate again. So that'll be 2, negative 1 over t squared, and 0. Okay. So here is our acceleration vector. So we need to, well, we're looking at the specific time when t equals 1/2. So I can go ahead and find a at 1/2. What is our acceleration at time equals 1/2? Well, it looks like 2, plugging in the 1/2, that'll be negative 4, and 0 doesn't change. So here's our acceleration vector. Some other things that we're going to need then, we need our unit tangent vector, So let's find our unit tangent vector. So remember, our unit tangent vector is our v vector divided by its magnitude. Okay. Well, again, we're talking about a specific time. We've already differentiated, so now we can go ahead and plug in that specific time. So our v vector at 1/2 is going to be 2 times 1/2, so that'll be 1. 1 over 1/2, that'll be 2, and the 2 is constant. And then the magnitude, so we'll just square them, add them, root them. 1 plus 4 plus 4, that looks like 8, 9. Square root of 9 is 3, so my unit tangent vector is going to be 1/3, 2/3, 2/3. So far, so good? Okay. So to get, a sub t, I need the dot product. I need how much of my acceleration is in this t direction. Oh, I've got a prime there. I don't want a prime there. Sorry. I don't know where that jumped in. Now my whiteout's not going to work. There we go. Okay. So my unit tangent vector, this has length 1, right? It's in the direction, right, of the velocity. And I want to know how much of my acceleration is in that direction. So I do that with the dot product, right? So the dot product tells you the amount that's in that direction. So I'll do A dotted with T. So 2, -4, 0, dotted with my T, 1/3, 2/3, 2/3. So that looks like 2/3 minus 8/3 plus 0. So that looks like that is -6/3, also known as -2. Okay, so this is our A sub t. That's the magnitude of the acceleration that's in the t direction. Okay, so if we think about, right, our two components, right, so we're going to break our acceleration vector into, right, that magnitude in the tangential direction times the unit tangent vector, and then a magnitude in the normal direction multiplied by the unit normal vector. Okay? So that first part, so A, right, I get my A sub t in the t direction plus A sub n in the n direction. We just found A sub t, -2. We found t, right? So this first part is going to be -2 multiplying in through that vector. So now we have to come up with the rest of it. Okay, so I'm going to scroll up here. So let's go ahead and write our A at 1/2. So 2, -4, 0 equals, I'm going to take my constant in, so -2/3, -4/3, -4/3 plus, right, A sub n direction. So, right, find the part I need. So I'm going to subtract this, right, subtract this one from both sides. So now I know that my A sub n direction is equal to, I'll go ahead and write it down here so that I can do my math, -2/3, -4/3, -4/3, and I'm subtracting. So I have 2 minus -2/3, so that'll be 2/3 plus 2/3, 8/3. -4 minus a -4/3, so -4 plus 4/3. What is that going to be? -12/3, -8/3. Just doing some arithmetic here. 0 minus a -4/3 is going to be 4/3. Okay, so that's this second part right here. So my A can be written as -2/3, -4/3, -4/3 plus 8/3, -8/3, 4/3, right? This is a true statement. If you add these together, you get back to your A vector. Oh, right there. But what we want to do is we want to set it up with this, like, do you remember the TNB framework, that Frenet framework? That's what we want. So we want to take that -2 back out and have that just multiplied by our T. And then I want to have that magnitude. I want to find this A sub n. I want to find the magnitude there and then put that in the direction of our unit vector, our unit normal vector. Okay. So here's, right, this second component is that A sub n in the n direction. So let's just find its magnitude. Okay. So we're just going to find the magnitude of this direction here, right, this vector. So that vector is what I got, 8/3 squared plus 8/3 squared plus 4/3 squared. So I'm finding the magnitude. So 64/9 plus 64/9 plus 16/9. Right, you know it's going to be pretty, right? I'll go ahead and grab my calculator just to make sure it's going to be pretty. So 64 times 2 plus 16 divided by 9, square root of 16. Hey, it's 4. Nice. So if I divide that by 4, then I'm going to get my unit vector, right? So here we go. Our A vector that we found before, right? It's 2, negative 4, 0, right? That's a true statement. I can break that up into the magnitude that's tangential, so negative 2 times the unit vector, unit tangent vector t, and then plus, right, the magnitude in the normal direction times the unit vector in the normal direction. So if this was the magnitude of my normal vector here, if I divide everybody by that 4, that'll make this also a unit vector. So I'll divide everybody by 4. So it just divides, right, the numerator by 4. 2/3, negative 2/3, 1/3. Okay. So this is negative 2t plus 4n. So we've changed from that XYZ coordinate system, right, that R was given in, and now we're just giving our acceleration in terms of the way that we're moving. So in the direction tangent to the way you're moving, and that normal component in towards the center. So another way to think about that normal component, I'm going to bring my page back here. That normal component, right, you can also find, because it's a measure of the curvature, right? So if you happen to know the curvature, right, a larger curvature, the tighter the corner, right, the larger that acceleration. I'm not finished. And then it's times the velocity squared, speed squared. Okay? So that normal component, right, you can change it by changing the curvature. Okay,